Hey, thanks everyone for joining. And my name is Adam. For those who haven't subscribed to our channel, please do join our channel, which is DevOps Learn Easy. Now, what we're going to do in this session? Uh, in this session, pretty much we'll learn more about how do you optimize your Docker image while you're using it in the production. But before we get started, now as we already know that almost every organization has started doing container-based deployments, which is the modern deployment. So they are not doing the traditional deployment where you take the application, you copy it to a machine or machines, and then configure and then start it, right? So instead of that, we simply create a container. So the modern way of deployment is using a container. So, which is where, how do you create a container? So, to create a container, basically you need an image, so which contains everything that is needed for deploying and running your application. So that's when Docker image is more of a read-only system, which has all those what you need. So by saying it, now what do you actually have in a Docker image? Now that's when Docker image is made up of different layers of files or file system. Okay. Now a best way that you can imagine this is like how you make a sandwich exactly. So now for a sandwich, you have various layers, right? So you would have bread, and then you would have your vegetables, and you put some kind of patty, which could be meat based or vegetarian. So basically, it has different layers. The same way, the image is made up of different layers. Now, what does that layer contains? So the layers, if you see, are the fundamental building blocks which consists of different files and the file system that is needed for your application to run. So that's where the important ingredient for your image are layers. And now, if you categorize the layers, right, you can divide or group the layers into three groups, or typically there are three types of layers what you can have in your image. Now, what are they? So the first and foremost layer that you would be having in your image is called as the base image. So, like how if you want to make a sandwich, you need the bread, right, as the base layer, and then whatever that you put between the bread is what makes a sandwich. The same way, if you want to create a container which has everything that you need, so the first thing what you need is the base layer, which consists of the platform necessary for running everything. So mainly whenever we say base image, it's the platform. So what do you mean by platform? The OS plus whatever the supporting libraries for the operating system. So that's how the base image contains more of the operating system and the supporting libraries for that. And then you put your application, which is the next layer, whether it could be a jar or a var or a Python based or a node based. And then between your base image and the application, you would have all those which are needed to support your application to run. So that is what we call it as dependencies. And again, if I compare it to sandwich, your base image acts like the bread, and your application is the actual sandwich patty, whether it could be meat based or it could be based on some potato or something more vegan. And what are dependencies? Dependencies are more like the supporting vegetables like tomato, onions, and spinach, or whatever that you want to support your sandwich, right? The same way. So now image consists of a layer called base image, which has more of the OS and the platform, and then your actual application. And between them, to support your application to run, you would have a layer of dependencies. Again, all of them are files or folders. Now, this is where, like for a sandwich, if you add more and more layers between your sandwich becomes huge. which is good for you to eat. But in reality, if I take an image and if I keep adding more and more layers, this is when your image becomes more blotted. Now, what are the concerns that we have if our image gets blotted? Because over a period of time, what we will be doing is we will be doing a lot of changes for our application to run in a better way in production. In that case, if you add more files and more layers into your image, the size of your image becomes very huge. So, what are the problems that we will have if the size of the image is huge? Now, not only the size, but the number of files and the layers what you have inside the image, if it is too much and if these are not actually needed, then that's where by having those unwanted libraries, your image becomes more vulnerable. And if it is more vulnerable, then you have to spend more time to fix it, right? And more testing is needed. And that's where more layers causes more security issues. At the same time, what happens now, once you create an image as part of your build pipeline, you need to upload the image to a registry, that is a Docker registry. Now, once again, the time that you take to build the image will also be increasing, which means your CI build pipeline or nightly build pipeline will take more time. And the time that you take to push this image will also be higher. And not only that, the last thing which concerns is when you are going to create a container, which is what we call it as deployment, it will happen in a cluster like Kubernetes. And that's where Kubernetes has to download the image from the registry. So bigger the size of image, then the download time will be huge. And now if I say deployment, the total time taken to download the image and start the application will be higher. And that's where in production, we need containers to be started as soon as possible. It's like seconds. And that's when keeping our Docker images light, at the same time it is less vulnerable, and removing the unnecessary layers is what we call it as optimizing the image. And that's exactly what we are going to learn and see in this session. Okay, and in this session we're going to discuss 8 proven ways in which you can optimize your image up to 95% so that it's more suitable for creating a container or deploying your application in a modern method in production. All right. So by saying it, let's get into these methods one by one. All right. So the very first method, use the base image. But what kind of base image you're going to use? So we're going to use a minimal base image. What does this mean? Now this is where when you try to create your image, that's your actual application image, if you just blindly take a base image which has unnecessary files and folders, then that's what is going to cause the size of your image to be higher and also more vulnerable. And that's where there is something called as a minimal footprint of every image. So if you take any image, there are a lot of variants of that image in which you would have an image with everything. You will have an image only with certain things what you need. So that way we need to find out what is the more optimal image which is useful for us, which has only the thing what we need. So that's what we call it as the minimal footprint. So that's when, now rather than taking blindly some image as a base image and then adding your application and dependencies will make your image big. So rather than that, choose a minimal footprint of the image which has only what you need, and later on if there is anything additional needed, you can add those files into your image. Okay, now a best example for this will be Alpine based base images, because Alpine based base images are very lightweight. Okay, now to understand this better on what do you mean by minimal OS footprint, let's take an example. Now, I've already created and started a machine in AWS and I have Docker installed. So I'm just directly jumping into this machine. Okay, so this is our controller machine where we are going to practice everything. And let me quickly show you. Do you have Docker? Yeah, we have Docker. And before we get started, let me delete all the images if I have anything here. Okay, so there's only one image. Now let me delete this image too. All right, so there are no images in my machine. So let's start everything from scratch. Right. This is the examples what we have. So let's go to the first method. Okay, now in this, I have tons of examples. So let's take it one by one. So now look at this file first. So this is an example of a blotted image, okay, where we will see how the size is very huge, where we have many unnecessary files. Okay, so in this example, what I'm doing, I'm taking a base image of Ubuntu 20, okay, and I'm trying to install MySQL in it, okay, and then all I'm doing is making the startup command for this container as the executable called MySQL. So basically, this image will have MySQL client, and anytime when I want MySQL client, I can create this container and use it. So now, in this example, we have taken a base image from Ubuntu 20, and inside that, we have added MySQL client. Okay. Now let's look at what's the size of the image for this. All right, now for this what we will do, we'll run the command docker build -t, and let's call this new image as image1, and let me tag it by saying m1. M1 means method 1. Okay, and since the file name is different, not the docker file, it's dockerfile underscore 1, so we will pass it as an option called dockerfile underscore 1 and space dot. In docker build, dot represents the context wherein all the source files from where you want to refer, that is the current directory. So let's go ahead and build it. All right, so now the image is created. Now let's look at the image. So you can see the total size of the new image is around 154 MB. Okay, for that we have taken the base image, which itself is around 73 MB, and then remaining around close to 80 MB we have added from installing the MySQL client. Okay, so out of 154, 73 MB is only the base image contents, and then whatever we installed the MySQL client is what is the remaining one. Okay, now how can we optimize this? And this is where, rather than taking a base image like Ubuntu 20, which has so many things which is not needed for us, if we take a image which has the less OS footprint like a Alpine based image, and then we install the MySQL client on it, then the total size will be drastically reduced. Now let's look at the optimized file. So the same example, my final goal is I want an image in which I should be able to run MySQL client. So instead of taking Ubuntu and installing MySQL, so you can see I'm taking a base image out of Alpine, and version doesn't matter, okay, for this example. And all I'm trying to do is installing the MySQL client, and then the same way I'm saying what is my startup command. Okay, so in both the first method where we use the Docker file and the same method with the minimal OS footprint image, that is Alpine. Now let's see what's the total size for this. All right. So I'll do one thing. So let's go back to the same build command. Now the file name is optimized. Okay. So, and I'll call it as image one opt, which is optimized. So now I'm building image one optimized for the method one, and I'm using the new Docker file, which is Docker file one optimized, which is this one. All right. So now let's do the build. Okay. So now let's compare the images. So you can see the same goal where we wanted an image in which you should be able to run MySQL client. So what's the total size of this image? It's just close to 40 MB, right? That's because the actual base image, which is coming from Alpine, which is around 5.6 MB, and on top of that you have added, so your actual MySQL is taking around 36 MB, right? So what happened to the remaining ones? The remaining ones are the OS. So that's where you can see, if you take any blindly image like Ubuntu image or CentOS or whatever, which has many unnecessary files, then the size will be too huge. And that's where, by taking a minimal OS footprint base image like Alpine and add only the things what you need, your image size is almost reduced by how many percentage? It's more than 80 percentage, right? So that's where always use a base image which has only the things what you need. Okay, which means which has only the minimal OS footprint. Okay, now that way start using base images like Alpine and then install whatever you need on top of that. So that way the total size will always be lesser. Now let's take another example for the same. Okay, now this is where, when you want to create an image for some kind of programming language. Okay, now when I say programming language, it could be something like Java or Python or Node or Go language. Now what happens, there is one more variant, or what we call it as the tag of an image, which is of a slim variant. So rather than just blindly taking any image, if you find out whether it has a variant of slim, then the slim variant usually has the minimal OS footprint. Because of that, the total size of the image will be lesser. So that's where, if you want to take some base image from your Docker registry, then search for those variants which are based out of slim variant. So once again, you will not be having all the unnecessary layers. So you can install only the things what you need later. Okay. So now for this, let's take the second example. So look at the Docker file. So in this example, what I want to do is just run Node.js. Okay, that's all. I'm not adding anything to it, but just as an example to show you, I'm taking the base image of node 16.19 and I'm just running the node as a startup command. Okay, so this is my very minimal requirement. So now if I create an image, this is when, so let's do this again. So Docker build hyphen t, and let's call it as image2 colon method 1, and the name of the Docker file is dockerfile2 dot. right? So let me show you the size of this image. So you can see the size of the image is 910 MB, because all we did is we have taken the base image of node and the tag is 16.19, which is 910 MB, right? Now the same, let's look at a optimized Docker file. Okay, so now if you look at this, this is where now I'm taking Ubuntu as the base image, but this time I'm not just going to take blindly any Ubuntu tag, but I'm going to search and use something called as a slim variant. So this is where, rather than taking something like Ubuntu, or rather than taking blindly CentOS or Red Hat or Debian, try to use the slim variant, which will have only the minimal OS footprint. So the same what I'm going to do, take the Debian Slim variant, and I'm going to install Node.js or Node 16. Okay, and the same startup command, which is what actually I've done in the previous Docker file. So now let's run this and see what will be the image size for this. Because rather than taking a base image of Node 16 directly, if I take a Slim variant and install Node.js, see how much of difference is there. So let's go ahead and build this again. So Docker build -t, we say image2 optimized colon method1, and the name of the Docker file is dockerfile2 optimized, and dot is the context. All right. So let me see the image size now. You can see your optimized image while taking a slim variant of Debian and installing the same node on it. What's the size? It's closely 238 MB. So again, how much you have saved? You have saved more than 60 to 70%. What? We didn't still add the application, but think, just by taking a particular base image which is having the minimal footprint, or taking a slim variant, you can blindly reduce the total size of your image from 60 to 80 percentage. Okay, so that's where it's very important that you should always choose a base image which has the slim variant or the minimal OS footprint. Okay, now the same, rather than taking a Debian slim variant, installing node on top of it, look at this example, which is the third example I want to show. So let's do a optimization of this image also. This is where, if you go ahead and take the slim variant of node, so go back in this first example, when I take the node tag is 16.19, the size is 910 MB, right? But the same node, if I take a tag of slim variant, instead of taking the Debian slim variant, I'm directly taking the node 16 slim variant. Okay, now let's see what will be the total size. So let me build this image again, and this time, okay, so the name of the Docker file is optimized 2, and I will also call the image as optimized 2. Okay, and let's run this. So let's look at the image size now. What do you see? It's 180 MB, which means rather than taking Debian Slim variant and installing Node on top of it, if you directly take a Slim variant of Node, whatever is available, then the size is further reduced. So now if you look at, you have almost reduced 90 percentage optimization, right? And that's where from now onwards, when you're creating image which is for a production grade, the first thing that you have to think and start implementing is use a base image which is something like Alpine or a Slim variant which has only the minimal OS what is needed, and then you add whatever is needed on top of it. Okay, so that's the first method. Now, before we go to the second method, let's delete all these images. So to delete all those images, I'll just say docker RMI, and I'll just say docker images AQ, and let's just delete it forcibly. All right, delete it. And now let's come back here. All right, and let's look at the next method. Again, another important method to optimize your image is what we call it as multi-stage builds. And most of the interviews, they might be asking you this question, which is the advanced side of Docker image. So pay attention. So let's say I want to create a image for a Go language application. Okay. Now this is where when you have some lightweight programming languages like Go language, now you have to first compile and generate the what we call it as artifact or the class, or typically it's more of your build output, which will be the binary file. Now this is where rather than building it on a server like a build server and then taking the artifact and putting into an image, another way what you can directly do is take this application, or not the application, the source code of the application, and you can compile itself directly inside your image and store the file. So this is one of the best way where I don't need a dedicated build server. I can do everything inside your container. And that's where, let's say there's such a requirement that I need, okay, in which we will try to take a base image from the latest version of Go language, and we will add whatever is our source code, and then we will do the build, and then you will have your application of Go language inside it, and then we can create the image out of this entirely by saying whatever the name you want, and that will run the application whenever we create the container. Okay, so that's what we're going to do. So let's come to the method 2. And now let's look at this example. So this is the example where we have a blotted image, okay, in which what I'm going to do. So I'm taking the base image as Go language, and then I'm trying to copy all the source code from my current directory to the image. So if you look at this current directory, I have some sample Go language. So let's not worry about this. You can take any Go language application you want, but I have a small web application, and this is the source code, and supporting it, these are the modules I have. Okay, so basically I'm copying all this source code into my image, and then we are compiling the code, and what it will generate is a Go language application called my Wezva app. Okay, and I'm exposing it to run on port 8080, and this is the startup command where it should run my web application. Okay, so this is what we need, so that my final image has the Go language application, which I can use it to run inside the container. So let's build this image. Docker build -t, So let's call it as image1 colon m2, which is method 2, and the Docker file name is Dockerfile1 combined, and dot is the context. All right. So we created an image, okay, and what's the size of the image? So the size of the image is around 860 MB, in which we have all the layers that is needed. Right now, basically just to show you, if I want to run this application out of it, I can just say docker run -rm -d, and I'll map 8080, all right, and the name of the image is image1 colon m2, all right. Okay, so we have this, and now if I just want to access this, I can just say curl localhost colon 8080. Okay, so this is what is returning me. So basically, it's just a small sample web application which is just printing some details. Okay, fine. Now let's not worry about the application too much. So let me just stop this. But so what is that we did now? If you come back and start looking at this side, so whenever you have such a kind of scenario where you have a lightweight programming language like Go language or Node or Python, you don't need a separate build server to compile. So you try to do everything inside your image. So in this way, it's very effective where you don't need a dedicated build server. But what are the problem in this? So the problem in this is you have the final image which is around 860 MB, and that has your application, but it also has unnecessarily the source code, and it also has the base image which is having something which is still not needed for your application to run, correct? And that's where the total size of the image is very huge. So what's the solution for that? Now, the solution for that is, instead of having everything in the final image, you can create a final image which will have only the application. But where am I going to do the build? So that is when, instead of doing everything inside one image, if you can think of an approach where you first create one image inside which you copy your source code and build it, and then like this, and then what I can do, so when I take an image in which I will put everything in it, and I will also build, and I will get my Go language application in it. So what we can do now is, you take a copy of this, but how do we take a copy of this? Is, we know image is read only, so we cannot take anything out of it. So we need to create a container out of this image, which will help us to access whatever the files that you want. So now you can copy the application which is running in that container to a host machine, and then we can create a new image in which we can take the base image once again as a image which has the minimal footprint of OS like Alpine, and add only the things that we need. So that way, rather than adding all the source code or everything that it has on the Go language base image, you just copy this. So the same what we have done in the first step, I'm dividing it into two steps. So this way, your final image has only the application. Now, what we have to do in this approach? So in this approach, we need to first create a image which will get all our source code, and it will build the app and it will be inside it. But to take it outside, we need to create a container, and from that we need to copy, and then we need to create another image inside which we will be able to copy, and all it will have is the minimal OS footprint plus to run your Go language application whatever is needed. So that way your final size of the image will be very less. Okay, so let's try to do this approach of building the image. This is where, let's look at this file too. So this is when, now let's assume the image that we have already built here is what we have. Now the only thing is, I don't want to run my application directly from this image because it's too big. So rather than that, let's take the copy of the application from this, and then we will try to create a new image, and that's what I'm going to do. Okay, so now assume you have copied the application from that image outside to the host machine, and now this is an optimized image where if I take the Alpine base image and I will install what is needed for running the Go language application, and then we will only copy our Wezva app and expose the port 80 and start. So this way your final result is an image which will have only your application and what is needed for that. Okay, now before we see it, now I need to have this application. Now this is available inside your image, that is the previous image, but like I said, image is read only, so you cannot copy or take anything from it. So let's create a container again and copy that. All right, so what we will do, let's run this command again. In this, we are going to create a container out of our first image which has the application, right? So this is running. Now, how do I copy a file which is inside the container to the host machine? There are various ways to do. Now you can create a volume and mount it in such a way that you can directly access, but volumes will always be expensive in managing. So instead of that, here I just want to copy a single file. So we will use a command called docker cp. For that, you need to know what file you want to copy and from where to where you want to copy. Now typically, let's have a look at our first docker file, which is combined. So you can see the file will be available under /app, which is where we are setting the work dir, right? So let me do that. So what we will do, if I say docker copy, okay, what you want to copy? So I want to copy the file which is available in this container. So give the container ID colon and the directory of the file, and this is the name of the file. So we are telling copy the file called app my Wezva app from this container, and where do I want to copy? I want to copy to my host machine in the current folder, so that now you can see the file has been copied. So this is one simple way as a hack you can do. Okay, so now what do we have? So we have our application copied, and this is where, if you look at the second docker file that I just showed you, all I have to do is take the base image of Alpine, add our app and create an image, and that's what I was just referring to in this diagram. Okay, so let's try this. So now let me build the image here. So docker build -t my image one optimized, okay, colon M2, and the Docker file, what we have is Docker file 2, context is current directory, so dot. Okay, so now if you look, the same output, wherein instead of having everything in one image, now you followed a process in which you separated the images, where in the first image you built the application, copied it, and created it a second image in which you have only the final application. So that way, what's the size? From 856 MB to close to 15 MB, which means it's greater than 95%, right? So this is where now, instead of creating everything in one image, you can create multiple images and try to achieve your goal. Okay, so this is one of a method, but following the method what we just now did, that is going through the process, if you understand, there is one Docker file which you have to create, which will do the build, and then you need to create a container out of it, and then you need to write another Docker file, and then you need to go ahead and create the final image. So this way, it sounds it's easy, but understand there are multiple Docker files you have to manage, and still you have multiple images that you are still referring in your registry or in your host machine. So that's when there will be too much of maintenance that you have to go through if you do this. So what is the best way to solve it? And this is when, on the latest version of Docker, instead of you creating multiple images using separate Docker file, Docker introduced a concept called multi-stage builds. And that's where, what do you mean by multi-stage? So whatever we just now did, instead of putting it as two Docker file, you can combine that everything into one Docker file. So that way, if there is an instruction which starts from the keyword called from, which means it is one Docker file equivalent, right? And that is what in a multi-stage build, it's considered as one stage. So a stage is nothing but equivalent of one image what you can create separately. Okay, but the benefit here is, by putting everything into one Docker file, Docker understands that you don't need all the layers. So whatever that you are building first will be tracked as a intermediate stage. Intermediate means it is only needed for a reference, and that is not going to be used for your final image. So that is where, unlike the previous method what we did, it is stored separately, whereas now your initial stages, whatever you're going to do in the Docker file, will be only for the intermediate purpose. So the same problem what we can do in multi-stage, combine it into one Docker file. But when you are combining like that, you need to separate the first Docker file content and second Docker file content with the name, and that is what we call it as stage one. So if I take now the first Docker file's content as stage one inside the Docker file. So what does the stage one contain? So all you're going to do is take the Go language base image, copy your source code, and build the code. Okay. But instead of you creating the image and then creating a container out of it and copying the file and then creating a second image, in the multi-stage, automatically once the first stage is done, you can go to the second stage. Now in the second stage, what you can do is simply refer to your first stage with the help of the name and give whatever the files you want to copy. So automatically the Docker itself will copy from the first stage to the second stage. Okay. Now this is where, here in your second stage or final stage, you take the base image of what you have with minimal OS and then directly copy from the first stage or the previous stage to your final stage. And from this, what will happen? If you create your image, your final image will have only the layer which is your Alpine base image plus your Go language application. So whatever that you did earlier with two Docker files and manually creating images and then copying the files by creating a container, you can do everything in one shot. So that's what is called as multi-stage build. Okay. So typically multi-stage build is a approach of building an image in which instead of having multiple Docker files, you put the content into one Docker file wherein each Docker file's equivalent is treated as a stage wherein the initial stages are more intermediate. Okay, so that whatever you have in the final stage will be converted into your image so that it will be more optimal. So let's have a look at it. So got disconnected. Let me connect back. Let me go to the method 2. So now look at this Docker file. So, okay, so what I'll do, just to put everything into a single line, let me delete the spaces so that it's easy for you to understand. I'll just keep only this space. All right. Okay. So now if you see, this was the very first Docker file we took. Now what is this going to do? It's going to take the base image of Go language, copy your source code, and it will do the build and it will generate the app. But the additional thing in the Docker file is for every instruction of from, you can consider it as a stage by giving a name. So that's where you're adding a new keyword called as the name of the stage. So I have referred it as stage 1. So this from here to here until you have the next from instruction, it will become one stage automatically. And now in the second stage or the final stage, we are taking the base image of Alpine, and this is where we are telling copy. Okay, and this telling the source is from this directory, but from where? And that's where we are telling from stage 1. So automatically what will happen? This will become our intermediate image in which whatever the content is there, you can still refer until the end of this Docker file. So that's how now this is what you will be converting into your final image. So this way of dividing the same Docker file by having multiple from instruction and giving a name wherein you can refer the content of one stage at any other stage is what we call it as multi-stage build. Okay, so this way now it's one Docker file, one command, and you are going to get your final image which is optimized. All right, so let's run the scene. So I'll say Docker build -t, and I'll call it as image multi-stage colon m2 and Docker file and colon 3. I'm sorry, got the context of dot. Now look at the images. So this is our final image, right? Wherein you see the total size is the same. So that's where multi-stage is very useful if you are trying to create an image for a lightweight programming language based application like Node or Python or Go language. It will be very efficient where there are two benefits. One, your final image will be built in one Docker file, but the other benefit is you don't need a separate build server. You can actually build your application in one stage and then take only the content of your application and put into your final image. However, you can also think of using multi-stage. If you want, you can do more things like in your build pipeline. If you want to do a small unit test, right, then you can also do a stage for that. So that way you can have one stage to build the application, one intermediate stage to unit test your application, and then you can also have one stage which will be having your final file. So that way multi-stage are an efficient way of building the images which can reduce the size of your application greater than 95%. Okay, now before we go to the next step, let's delete all the images. But there's one thing that you need to note here. The intermediate layers. Now, this is one issue with multi-stage. Even though your final image has only the smallest layer what you wanted, still for every intermediate stage, whatever it is creating, the images or the layer of the image is still stored in your where-lib Docker. So generally, this is what we call it as dangling images, okay, or images which is not referred anywhere. So always it's a good practice that you delete these kind of images later. Now for that you can just go ahead and say docker image prune. Okay, that's all. Now what will this do? This will go ahead and delete all the unreferred images because these are intermediate images which is not referred anywhere, or technically we call it as dangling images. Okay. So maybe if you are trying to automate your image creation using your CI/CD pipeline, what you should do after doing a Docker build command, you should go ahead and delete all those dangling images. Now again, this might be an interview question when someone asks. So whenever you create a multi-stage build, all those intermediate layers will be still stored, but it will not be referred anywhere. So it's always a good practice to delete them, which is not needed later. All right. Okay, so to delete all the images, I can just say the same command docker rmi and I'll say -aq. I still have this, so let's stop this also. Okay, so I don't have any more images for this method. All right, okay, that was your second method called as multi-stage. Okay, so let's look at the third one. So what is this third method? Minimize the number of layers. So it's again like a sandwich. If I buy a sandwich where there are too many layers, the cost of the image will be higher, right? So what if I want a image which is just very lightweight? Then I shouldn't be having too many layers to it because every layer is going to be charged for you, right? So the same way in a Docker image, what happens? Your image is consisting of different layers, but what you also have to know within your image when you are trying to build it through a Docker file, and for that if you try to use some instructions like run, copy or add, every time you invoke this instruction there is a new layer created. Okay, So if you try to run the instruction called run 3 times separately, then there will be 3 layers created. Or if you are trying to copy some multiple files and you are using copy several times inside your Docker file, that many layers will be created. Now, what will happen? For each of the instruction what you are doing, there will be a separate layer created. And this is when for every layer that you are creating, there will be the size of the image getting blotted. So what we have to do is we need to reduce this number of layers by consolidating this. So typically when you are trying to use copy or add, instead of using multiple times, try to consolidate and use it one time or consolidate it. Now, same way, if when you're trying to execute some OS commands inside your image, instead of using several run instruction, consolidate and put together as one run instruction so that the number of layers will be reduced and there will be the size of the image optimized. Okay. Now, to understand it better, let's take an example. Okay, now the example that I'm taking you might not be showing a great reduction in the size or optimized image, but typically this is going to be one of the way that you can see that you can be getting a better image. Okay, so first let's look at this file. Now, what do you see in this example of the blotted image? So I'm taking a base image of Ubuntu and I'm trying to do a apt update, upgrade it, install a package like vim, nettools, and then DNS utilities. Okay, which is correct. But when you try to run this, it is going to typically create an image with more layers, and obviously the time that is going to take to build every layer will also be higher. Okay, so let's see that. So what we will do, let me run a command called time and capture your total time. So docker build -t. So let's call it as image1 method 3 and -f the docker file 1. Okay, so now roughly it took around 40 seconds for us. Okay, and docker images. So the size of the image is around 237 MB and it took around 40 seconds for us. Now, how do you know what are the layers available in it? So for this, there is a command called docker history and you can give the image name. You can see it has many layers, and roughly for this example where all we did is took the OS of Ubuntu and then we just installed all of them, it took close to 40 seconds and it has like around 10 layers inside it, right? So what's the best way to optimize it? And this is when, if you look at this Docker file which is optimized, I am consolidating all the run instructions using one instruction, wherein I'm combining all the OS command with this ampersandage. Okay, so what will happen now? I'm doing the same stuff. I'm taking the base image of Ubuntu and I'm trying to run all these commands inside my image, but it is going to create only one layer. Okay, so ideally the total time taken and the number of layers should be reduced. Now, you will not see a huge difference, but definitely there is some difference which you can understand because it's just a small example. But if you try to compare it with real time, when you have some more complex things to run, then each layer reducing will be of great efficiency for you at the later stage. But let's look at the difference now. So let's go back to the same thing, time, Docker build, and I will say image1 optimized, method 3, and the name of the Docker file is Dockerfile1 optimized. Okay, now you can see there was not a big difference, but ideally there was around 4 to 5 seconds difference. And yeah, the image size will not be that difference, but at least you should see around some 5 MB of difference is there. But look at the Docker history and look at this image now. So the number of layers what you have is again reduced by half of them, because instead of having 5 run instructions, I just had 1 run instruction. Okay, so that's where. Now the method 3 is how do you minimize the layers. So to minimize the layers, first thing you can do is consolidate multiple instructions like run, copy, or add into one instruction. So that way number of layers will be reduced. So obviously number of layers is reduced, the time taken for the image creation and the size of the image and the number of layers will be reduced. Now let's take another example to understand this. Okay, now the same thing what I'm doing here in this example is I'm just trying to create a container in which I am just creating a file called ABC in which I'm running 3 separate run instructions. Okay, now what will be the optimized of this? So if you look at the optimized way, instead of running several run instruction, I can just execute everything together in one run instruction. But this is where you need to combine multiple OS commands into one execution using something like the ampersand. So this is the shell operator which will help you to combine multiple OS commands. Okay, so like this, any kind of OS command that you are trying to execute using the run instruction, instead of having multiple run instruction, try to use one instruction which can combine multiple OS command. Okay, now let's look at another example. Okay, this is where again I have a example of blotted image in which we are trying to have a Ubuntu base image, and then I'm trying to do apt update, and then I'm trying to do apt get install of a package called netcat. So what will be the ideal way or the optimized way of it? Okay, so instead of running several instructions like run, so I'm just going to combine it together into one instruction. Okay, so this is how. The third method, what we are going to do is minimize the number of layers. Okay, so that way, so far what we have seen is 3 proven methods. One is to try to take a base image which has a minimal OS footprint, in which try to use image like Alpine, or try to use a slim variant of your image which could be a OS based image or directly a programming language based OS, in which slim variant will reduce the total size more than 80 to 90%. Then the second method is, if you have a lightweight programming application, instead of having several images and several steps of Docker file, you can combine all this Docker file into one file in which every equivalent of a Docker file will be created as a intermediate stage, which can be used later, so that your final image will be lightweight. And the third method, what we saw, is the number of layers has to be reduced. All right. Now, let me continue on the remaining steps or the methods on the next video. Thanks for watching.